in the previous lecture, I constructed the solution of the Dirac propagator with the boundary conditions implied by causality, and that basically gave an I epsilon prescription such that the propagator vanishes outside the light cone. So, this formulation is known as Stuckelberg Feynman interpretation, which essentially amounts to particles go forward in time and antiparticles go backward in time, and in particular we have chosen the convention that they will have opposite value of p and s compared to the particles when they travel backwards. And this interpretation and the propagator language was introduced first by Stuckelberg, but not many people paid any attention to it. It was independently reformulated by Feynman, and he went further and heavily used it to do many practical calculations. So, more commonly it is basically labeled as Feynman's method, and he also invented a diagrammatic language which makes this interpretation very easy to visualize. We will see the details of that particular language today, in particular introduce the interactions of electrons with the electromagnetic field and see how the propagator gets modified because of this particular interaction. To revise, let me just write down the breakup we achieved using projection operators, that the total wave function was the plus component, which essentially amounted to taking the modes with positive energy, and minus component which amounted to modes with negative energy. So, this was just a convenient breakup, but the two modes with different signs of energy propagate differently. So, it is useful to separate this thing out. Afterwards, now I can write independent equations for evolving both these modes, which are the same equation written together, but now projected into two different components. So, that two components evolve as positive energy goes forward in time. So, one can use this step function, and that is the definition of the Green's function. Multiplied by gamma 0 psi integrated over d cube x, and gamma 0 essentially is the operator which separates the positive and the negative energy parts. In the covariant language, it appears automatically to connect between psi plus projection, and the total wave function which is psi. It is essentially also connected to the reason that if you calculate overlap for Dirac propagator, you have to use a psi bar psi structure and not psi dagger psi, and that extra gamma 0 is responsible for producing the bar in this expectation values as well. So, this is what happens to positive energy part, and the negative energy part has a similar formula. It now has a step function with opposite sign, and now one can write a minus I, because I am going to reinsert this gamma 0 again, and gamma 0 for negative energy gives a minus sign which is put in front of this equation with a minus I, and one has the analogous evolution of the negative part. So, this is a description of a free Dirac particle evolving in accordance with the principle of causality. Now, we can bring the interactions in. The full equation is only slightly different than the free particle equation, in the sense that instead of the free Hamiltonian H 0, now we will use the full interacting Hamiltonian, which is H 0 plus H interaction. So, one can again write down the equation in presence of interaction. The full propagator, which I am going to denote by SF with a tilde on top, and it satisfies the equation which is the free part unchanged, but now it is acting on this full propagator Hamiltonian with interaction. I am going to write it on the other side of the equation, and this can be written as the delta function plus the extra term, which is, I will just write it schematically, interaction, because this equation is written in the Lagrangian formulation and not the Hamiltonian formulation, acting on this SF tilde, which was on the left side, but now you moved it to the right side, and this is a generic structure, and knowing all the detailed formulation, this result can be rewritten as integral d4 y using an auxiliary variable, and the first term I am just going to rewrite in a clever way. So, when integrated over y, this product of two delta function just produces delta 4 of x prime minus x. That is a trivial part, but now we have the full interaction term in the Hamiltonian. In this Lagrangian operator, that interaction term was just obtained by changing p slash to p slash minus e times a slash, and e times a slash I am going to rewrite on the opposite side of the equation. So, that now becomes e a slash at location y, and then S f tilde y x. So, this is a general result which says that from x to y there is a propagation, then there is a interaction at y could be any point in the whole space time. So, it is integrated over the whole space time, and then there is a delta function which describes the connection between y and x prime. So, it just puts in this extra interaction at this location x prime equal to y, and that gives a modified propagator equation. If you do the trivial integral here again over y, it will become E a slash at x prime and s f tilde also from x prime to x, which was exactly the operator on the other side of the equation with argument x prime. So, this is the equation, but now we have a form which can be related easily to the free particle propagator which we calculated. S f is the solution that has only delta 4 of x prime minus x on the right hand side without any interaction. So, this S f tilde has an extra term which can be easily verified. It is a solution corresponding to the first term, which is S f. This operator acting on S f gives the delta function, but we need something extra which gives the remaining piece, and that part can be rewritten in terms of S f as well, because the delta function is again cleverly utilized for the purpose. We have this delta for x prime minus y converted to S f of x prime minus y. The remaining stuff is already in the correct form, and this is the formal result. So, if you operate by this operator del prime size minus m on both sides of the equation, every time it acts on S f, you get delta functions, and it exactly amounts to the structure which we wrote above. So, if you are given an answer for S f, which we already calculated in the previous lecture, now we can obtain an answer for S f tilde. This procedure is at this stage formal. It can be easily iterated in a perturbative framework, where in the leading solution you start with ignoring interactions. S f tilde is equal to S f. At the next order, S f tilde is equal to S f plus E integral S f a slash another S f, that is the next order. Then you take that whole expression, again substitute on the right hand side in place of S f tilde, and you get expression which is correct to second order, and so on and so forth. This is now a general solution for a propagator in presence of interaction. One can also write a similar expression for the wave function in presence of interaction, the same interaction, the solution of the Dirac equation which is now of the form again denoted with tilde. The purpose of this tilde was to take the interaction term to the opposite side of the equation, and this structure in this Lagrangian equation is just E a slash and psi tilde. So, the free part is on one side, the interaction part is the other side. Again, in the terms of the propagator language, we just have to treat this right hand side as a source, you know what the propagator is, and then insert it back into the equation. So, the general solution is psi tilde x, psi x is the solution of the homogeneous equation when the interaction term on the right hand side is 0, and the contribution now is coming from the interaction term overlapping with the corresponding Green's function. The Green function corresponding to the left hand side is nothing but the propagator, but without interaction. So, this is actually SF and not SF tilde, and the complete expression is this, where psi tilde now appears on the right hand side as well. Again, this is a formal expression, but if you want to use perturbation theory, we can iterate it. The leading order is just psi tilde equal to psi. At the next order, psi tilde will be psi E integral SF a slash psi. Then you can take that whole expression and again put it in terms of psi tilde to get accuracy to next order, and so on and so forth. So, we have a complete procedure, the iterative procedure provides results for so called scattering problems, because we are dealing with these asymptotic states which are plane waves, and the solutions are now going to arise as powers of what is there on the right hand side, and the power is easily counted in terms of the electromagnetic coupling. And we have the value E denoting its strength. So, this is a whole formulation and it works very well, and we will see how it works in many different instances. Again, one can define a so called scattering matrix problem, where all these things can be converted easily to matrix elements between certain initial state and certain Feynman states. Are the components of wave function propagate from t equal to minus epsilon f infinity to t is equal to plus epsilon f infinity. Now, this epsilon f was the symbol which we had used to denote the sign of the energy. So, this is another way of saying that the particles with positive energy are going to propagate forward in time and the ones in negative energy are going backwards. In that convention, the matrix element can be written as S F I. This is schematic, but we have been using it. It is defined as the overlap of certain final state with whatever solution that has evolved from the given initial state, and that solution we have denoted by psi tilde. So, this is just a definition, and one can easily now evaluate the overlaps. The leading term of psi x just produces a delta function, and I can just abbreviate it as delta of some final and some initial state. But then the second part now explicitly gives the overlap, and that can be now written as I epsilon f d 4 y psi f bar y e a slash psi tilde of y. The extra sign of epsilon f is a result of using this propagator S of x minus y together with the buried factor of gamma 0, which is part of psi f bar. This is again a formal expression. If you can calculate this kind of overlaps, you will be able to calculate the scattering matrix element. The only way one can do practical calculation is in a perturbative expansion, where psi tilde is rewritten as psi plus some corrections, and then you evaluate these objects term by term. So, this is a important description, and one must remember that the covariant expressions for physical observables result only when both particle and antiparticle modes are included in the analysis. The consequence is that if one calculates only one part, saying only the particle contribution, the result will not be following the restrictions of Lorentz invariance, or if just antiparticle is included, the same thing, both of them are combined together with the appropriate sign changes, and then the total result will be Lorentz covariant, which is our requirement for implementing fully relativistic analysis together with causality. Now, let us describe some of those things in terms of what are known as Feynman diagrams. These are nothing but space-time pictures representing interactions in a perturbative framework. This has gone much beyond the theory in which they were invented, namely quantum electrodynamics, but in QED as explicit expressions. So, they are an alternating sequence of propagators and interaction vertices. One is quite accustomed to saying that a particle propagates from this location to the next location, has an interaction there, then it propagates further to a third location, has another interaction there, and so on and so forth. This is a loose language, not strictly in accordance with the restrictions of a genuine quantum theory, but it expresses in an intuitive fashion very easily what all things are happening, and so it is also a very popular language, even though it is a loose description. It is heavily used in terms of doing the calculations, in the sense that to do the calculation one actually starts out by first throwing all the Feynman diagrams, and then for each Feynman diagram writing the corresponding algebraic expression and adding those things up. Because writing the algebraic expression from the beginning generally turns out to be quite cumbersome and messy, and this way you can remember the things very easily and count the various factors of propagators and vertices and corresponding operators in a straightforward manner. The fundamental structure in quantum electrodynamics is just 3 lines. There is a incoming propagator, there is a outgoing propagator, and there is a vertex which represents interaction with the electromagnetic field. So, this is SF, this is SF, and the vertex is represented by E times A slash. This is generalized further in a full theory of quantum electrodynamics, where the interaction vertex is interpreted as interaction with a photon, and the wavy line which I have drawn here then will become a photon propagator, but we will come to that when we discuss the dynamical behavior of photons interacting with fermions. Right now, the vertex can be just the interaction of a fermion with a background electric field represented by E A slash in terms of a operator structure. This is a basic unit, and as I said, by repeating this one can have different descriptions in terms of how many orders of calculations you want to do. Now, this description certainly has one feature which is expressed here by the arrows. So, the arrows describe evolution in time. So, in particular for every propagator there is an arrow which says the particle is going in the future in this direction, and in this particular picture the time direction is sort of pointing upwards and the space is in the orthogonal direction, which describes many different locations, and then one has this representation of a interaction. And it is here that the interpretation of particle and antiparticle also re-enters the language, in the sense that an antiparticle will have the same kind of diagram with the arrow pointing in the opposite direction, which amounts to flipping the sign of the momentum, energy as well as the spin, and it will be denoted by an appropriate change in the expression for SF. So, one can have two different descriptions. The processes involving antiparticles can be understood in two different ways. Here it is much easier to illustrate by examples. I will just draw simple diagrams. One prescription of this interaction, suppose, has a diagram of this particular type, where an electron comes in, it scatters at one particular point, goes backward in time, in the sense that its energy now is negative after the scattering, and then it rescatters, and then it goes forward in time with certain positive energy. This description uses only electrons, but with two signs of energy, and with this Feynman-Stuckelberg interpretation, which we have already built inside our formulation, the same diagram can be now drawn with arrows pointing opposite way for this intermediate segment. This will have a description that in the initial stage there is an electron which propagates to point 1. At point 2 there is a production of E plus E minus pair out of nothing, that is the vacuum, and this pair production is allowed by quantum mechanical uncertainty principles, provided this is short lived enough. So, it does not last forever, it is not going to produce asymptotic states, but one of the particles can be asymptotic, can go to infinity, and that is the second E minus. The E plus which is produced in this pair production now can annihilate with this E minus coming from the initial state at point number 1, and there the annihilation now goes back to vacuum. The E plus is a short lived intermediate state, but now it is appearing here as a positive energy solution, because when you use physical E minus and E plus particles in these diagrams, both of them will have positive energy. There are no negative energy counterparts. Here there is negative energy and all E minus, and here there are only positive energy states, both E minus and E plus. And the way we have constructed the formalism, these two descriptions are completely equivalent. One just has to remember the rules of what is a electron propagator with negative energy is going to look like, or equivalently what is a positive energy positron propagator going to look like. They will both look identical, and so the factors describing the various segments of this Feynman diagram produce the same result. A similar description can also be given for processes which involve loops. The most simple example of such an object can be just two segments it could be either an electron going around in a loop with two interactions, and this is certainly allowed because the interaction can absorb the energy to convert positive energy particle to negative energy particle. The alternative description of this process will look like both electron and positron moving forward in time. There was a pair creation at one point, and there is a pair annihilation at the other point. Both this result give identical answers. One can add a little bit of mathematics if one wants to see this explicitly. So, let me just describe the two languages in this simple pair production example, and I will just describe the various plane wave phases without worrying about interactions and normalization factors. The first language is of electron going around in a closed loop. So, it can be represented as one electron with positive energy in the final state. It is produced by some interaction from another electron which has negative energy in the initial state. That is the description of what happens at one particular vertex in this diagram, say point number 2. In this picture, there is a initial electron with negative energy getting converted to a final electron with a positive energy due to some interaction. Now, one can plug in the plane wave factors in this description. The final state electron will have a wave function u bar with some momentum which is p minus, minus here refers to that it is an electron, the interaction will be something of the nature A slash, and then the initial state is a negative energy electron, and we saw its fundamental variable was this wave function denoted by V. It has a energy momentum which I am going to denote by P plus, because it is describing the antiparticle mode, and P plus is just a label for this particular language. Then by plugging in factors, this object is going to behave like e raised to minus I p minus dotted with x, the whole thing complex conjugated, and then e raised to I p plus dotted with x, because that is the behavior of this wave functions V. U and V have opposite phases. This is one particular language. The other language is similar, that corresponds to now writing that there was nothing and the pair got produced out of it. So, now you have an electron in the final state with a positive energy, as well as a positron in the final state with a positive energy, with interaction and produced from the vacuum. The behavior of this is now both particles of positive energy are there in the final state. So, it is e raised to minus I p minus dotted with x, then e raised to minus I p plus dotted with x. P plus is momentum of the positron, but now it is in the final state. So, it comes with the opposite sign of the phase, and this whole thing is complex conjugated. So, this is a description. What one can easily see that all the phases and the signs of momenta between particle and antiparticle are arranged in our convention, so that both these descriptions produce the same mathematical expression, even though in one case we are writing some object in the initial state, in other case you are writing the antiparticle in the final state. This illustrates a symmetry which I had mentioned. This equivalence is an example of crossing symmetry. It is something which we had seen in the discussion of Hole theory, that you can change the particle from an initial state to an antiparticle in the final state, flipping the signs of all momenta, and we can easily see that illustrated here, both in terms of the matrix element as well as in terms of the Feynman diagrams. This is a very useful construction and terminology which is heavily used in calculations in perturbation theory. The generic procedure in calculations is to draw all allowed Feynman diagrams and sum the results. This procedure includes summation over both particle and antiparticle modes as well as interactions occurring at different location in space time. One has to remember the rules of statistics also while summing over this particular processes, in the sense that some diagrams might be related with some other ones by interchange of particles, and when you interchange the particles in this particular diagrammatic language, it corresponds to interchanging lines that will incorporate the Fermi or Bose statistics as the case may be. So, when you add the diagrams, you might have an extra sign coming from statistics. In the particular time ordering part, the illustration is that the total result is of the form where all possible geometries of this propagators is included. In particular, this intermediate points 1 and 2 are going to get integrated over the whole space time. Their locations are not restricted, they are the interaction positions, but the interaction positions could be anywhere, and so they can be ordered either in a situation where 1 is in the future of 2, or it could be that 2 is in the future of 1. When one sums over all possibilities, one has to include all these different orderings simultaneously, and the total object will be the sum over all possible interactions, or in other words, it will include all these propagator lines irrespective of whether they are going forward or backward in time, when we draw all combinations and then adds them together. In this particular case, these two different ordering combine. Both pole contributions for the propagator between 1 and 2. In practice, this sort of happens automatically because of the algebra which we have constructed with the prescription of I epsilons, when one has 1 over p square minus m square regulated in terms of two different poles. It can be written as a positive energy pole plus a negative energy pole, and as long as one uses this total combination, these objects is equivalent to the sum of two contributions, where the first is a positive energy pole, so it corresponds to a particle going from 1 to 2 evolving forward in time, and the other one is the same thing, but it is a negative energy part, equivalently the antiparticle corresponding to evolution backward in time. When one uses this total Lorentz invariant combination p square minus m square, both these things are automatically summed, and one does not have to worry about this two different diagrammatic orders when one uses this covariant expressions. That is useful in keeping track of what all things are calculated and what have to be combined when doing detailed calculations with what other contributions. It is generally always useful to combine various contributions to get quantities which are Lorentz invariant. We will see that this thing will generalize to other possibilities where the interactions with photons will come with extra symmetry called gauge symmetry, and in those cases again it is very useful to combine all contributions which are gauge invariant together. Those calculations then provide important checks of symmetry and whether the calculations has any inconsistency or error inside them or not. This is all the machinery. I just want to add one more comment, that in these diagrams fermion lines do not end. They always need to be continuous. So, they either go from the initial state to final state or form closed loops. This is an example of the superselection rule which I mentioned while describing Lorentz symmetry, that the bosons and fermions form different sectors. The vacuum belongs to the bosonic sector and a single fermion belongs to the fermionic sector. There is no way one can superimpose one with the other. So, if the fermion has to be there, it will go all the way from the initial state to final state remaining in the same fermion sector, or otherwise the closed loops will involve particle antiparticle creation and annihilation, where one can mix fermion with bosonic sector, but only in pairs. That is a topological feature which is buried inside this diagram. On the other hand, photons, which are represented by wavy lines, can appear or disappear out of basically nothing. That is allowed because they are bosons, and so in the same sector as the vacuum. This distinction is also buried inside this particular diagram, the feature that is useful thing to keep in mind is that two differently ordered fermion contributions show sign difference which is in some sense connected to the Pauli exclusion principle. It is part of this particular algebra because we are viewing a single fermion going both backward and forward in time. If you look at a fermion line which intersects a particular time slice at 2 points, one can see that one of them is a positive energy electron and another is a negative energy electron. Since it is the same fermion line, it should obey the principles of Fermi statistics. In particular, if they are interchanged, there will be a negative sign. One can also look at the diagrammatic representations where the 2 points are interchanged. In that particular case, corresponding to 2 different orderings, the algebra we have constructed is such that the negative sign already is built inside the various definitions of propagators between positive energy solutions and the negative energy solution. But this will become very explicit in detailed calculations later.